Okay, thank you very much. Hello, everyone. Today I will talk about the charge lepton Fourier variation at the EIC. This talk is based on this paper with Vecino, Curry, Chris, and Emira. The lepton Fourier variation is not conserved. We have known this a long time ago because from the neutrino isolation we know that the different flavor could change to each other. For example, the mu e could be mu mu or mu tau. This observation also tells us the neutrino has a small mass. So after we include the neutral mass term, in principle, we could also generate the charge lepton Fourier variation in a standard model. This is a typical example of the tau to E gamma. And then we can use a mass term in here. So you could generate the charge lepton Fourier variation. But in the standard model, this branch ratio is highly suppressed by the neutral mass because it's typical the branch ratio is mu over mw square. So that's roughly 10 to the minus 44. And this small branch ratio would be very challenging to test this charge lepton Fourier variation in the current or future experiments because this branch is too small. Due to the standard model, the branch is too small. So in this process, we are also sensitive to many new phase models. For example, maybe some new phase particles could contribute to the tau to E gamma stress loop level. Oh, sorry. And then we could test the new phase through this charge lepton Fourier variation process. On the other hand, due to the charge lepton and the neutrino is the doublet on the standard model. So the signal also could be related to some neutrino mass models. For example, the tree level or loop level. For example, in here, I just show about a few years ago, we proposed a model which could generate the neutrino mass at loop level, and then also could induce some charge lepton Fourier variation. So precise target signal are very important for us to do fix and also to test the neutrino mass generation mechanism. And for the charge lepton Fourier variation signal has been widely tested at a different level. Here I just focus on the tau lepton because the muon signal has been highly constrained by the neuron data. So there are many data could constrain the signals from well-known observables. For example, the BABA and BER2. They search some signal from some meson decay. The meson could decay some to tau E, and for example. And also, for example, the lab, they could decay some to tau E gamma or tau to pi pi. Tau E to pi pi. And also the HERA and also Teltron HC also search this charge lepton Fourier variation. In the next talk, I will study the possibility of the EIC to constrain this signal, and also try to compare what's the sensitivity to other limits. Here, I just show first the graph picture to let you know what's the main conclusion for the EIC. For the light gray is for EIC and tau to mu, and the blue is for HC, and the red is for the longitude data. So I just use some typical operator to show the results. You could find out the EIC is compared to HC. You can find light gray and blue, almost same, not change too much. So the EIC is very important to get a constraint for this kind of new phase models. I will discuss the detail in later. So next, I will discuss the tools what we will use to describe this charge lepton Fourier variation. Firstly, we assume the Higgs is the EFT. It means we can use Higgs is a fundamental particles, so we can use the linear EFT to describe the signal. And after we integrate out the new particles, then the new Higgs could be described by the high density operators. I think many people have discussed the EFT. So here this is times 6, and that's our 8 operators. And for the relation of four cellular and EFT, I think it should be also well known. In the high energy scale, we have both the light and heavy particles, but in the low EFT, we only have light particles. So we should integrate all the new degree of freedom and then could get a matching to the large EFT. This is the whole picture of the EFT. In our study, we consider the general operators. It means we include all possible dimension operators which could generate the Lepton fluorescence. It could include the vector and actual currents operators and all type operators and count type and the four-Fermi operators. Here just show one type of the example. And then this is for the vector and actual current and also the type operators. For the four-Fermi operators, we also assume a general quark flavor structures. It means which includes the DD, DS, DB, and also SD and SSB, and also and all the possible quark flavor combination. This is our theoretical assumption. Because we try to compare from the knowledge data to hand data, but you know from the knowledge data, the typical scale roughly about few GeV, for example, mass determined by the mass on tau mass, so roughly about few GeV. But for HC, this could be a few TeV. So the Agiloni effects are very important. We should include the Agiloni effects when we compare the different limits from different experiments. On the other hand, when we include Agiloni, is a different operator will mix into each other. And for the knowledge data, although they will not drain the heavy quark component directly, for example, top quark, because the energy was low, so we cannot constrain the top quark component directly. But through the Agiloni effects, they will also give some strong constraint because the data in the knowledge is really, really precisely. So we could give some constraint. So the next I will discuss the details of our study. For DS production and the EIC, in general, for general precision of the electron and the proton, we have the cross section could be could contain two parts. One is for the unpolarized cross section, another one is so-called the polarized cross section. Polarized cross section depend on the polarization of the proton. From any study by this group, you could find out the unpolarized cross section will always dominate the cross section because for this one is for the polarized PDF is the unpolarized PDF. If we find for the polarized PDF, the PDF is much smaller compared to the unpolarized case. So due to this reason, the cross section for the unpolarized cross section is always larger than the polarized case. For example, the NC is neutral current. So you could find another roughly about a 10 effect 10 for the unpolarized cross section, larger than the polarized case. So in our study, I will focus on the unpolarized case. Even we include the polarized cross section, we will not change it too much. Based on the decay mode, for example, tau could decay to electron and muon, and also the hadronic decay. We have 3 channels. And of course, the background in this process is the standard model DS production. But for the electron and the hadronic decay channels, after we include some chemical cuts for the PT and PT and also messenger, the background is also very large. So the cut frequency typically is 10⁻⁴. So, but it's not enough to suppress the background compared to the signal. But for the muon channel, the situation is very different because after we require a hard muon with the PT muon larger 10 GeV, the cut efficiency will change roughly about the temperature is roughly about 10⁻⁵. So after we include other like the PT, Lepton, and also misenergy, this process roughly almost the background free process. So we could give a very strong constraint for the charge Lepton fluorescence with the tau decay to muon. Of course, for the tau to hadron, the blood pressure is large. So you want to use this data, in principle, you should include other technical, maybe some jet subtraction information and so on. But in this study, I will only focus on the muon channel because we only include some very simple cut to separate background. After improved cut, we could get the cut efficiency, because this is very very important number which we are used to constrain the operators. The conclusion is not the cut efficiency is not sensitive to the quark flavor in the short state, because for the C quark and because the UD and UD quark they could have the large PT could be gen large PT of jet, but for the B on the C they do a small PT. So it was sensitive to the different flavor you can find from the U0, CC, DD, and SSB. The efficiency will change a lot. But we are not sensitive to the pressure of tau. For tau is left or right, doesn't change too much. For example, this is for the CLQU and CIEU. For same interested flavor, the efficiency doesn't change too much. So almost same. So after we know this color efficiency table, we could give a constraint for the Church-Lepton flavor operators. I will summarize all the constraints in the later. And next, I will discuss other constraints. The first one is from the HC. Because the HC has large data, huge data, so you could give us some constraint for the for this kind of signals. For example, you could constrain for the vector and actual current type operator for the Zipf decay, to the tau, and also could get constraint from the type operators from Higgs decay tau. And also you also could get constraint for the Fermi operator from top decay, and also from the JM process. We could also constrain many operators. So we in our study we also include all the possible constraints from HC. On the other hand, a very important constraint is from the orange data, because the limits could be very strong. For example, we could include the tau decay and also the mason decay. Because the lepton neutrino is a double-slit, so some process could also give constraint, for example, pi to E mu, but they don't relate to the tau directly. We call this as an indirect bounds. So we also include all the possible constraints from the like pion, cation, and dion, also some B meson and so on. So here is a typical diagram to show how those operators will change the decay branch ratios. For example, you will change the tau to E gamma and through the carbon directly, and also for the other diagram. So here I just come back to our first conclusion. As I said before, the light gray in here is for the EIC and tau to muon, and the blue is for HC, and the red is from the large data. And the conclusion is not the EIC is comparable to HC. Of course, here we just use the luminosity is roughly about 100 US per bar example. Because in the future, maybe you could get more data, so you could get a stronger limit. I also tested the limit from the hydro decay, but I assume the cut efficiency is equal to 1. That's just as to show what's the best we can do. So you could find out after maybe a few times limit improvement could be good from this one. So it's very important to constrain this kind of near field models. This is for dipole E-cover and also vector and actual vector current operators. We also tested the four Fermi operators. For example, in here, the conclusion is that the Higgs quark components will give the EIC could give a very strong constraint for the Higgs quark components. That's for the light gray. And the limit is could be comparable to the HC and even for the non data. And I said before, the arginine effects are very important. For example, in here, the tau to E pi pi, although they will not relate to the B quark component, but through the arginine, the non data also could get some constraint. But the capital analysis, we only assume only one operator at a time. But in some new physics models, when we integrate some new particles, it could generate more than one operators. You to only maybe only some few, maybe only for some special case you only generate one operator. So it's very important to consider that after we include more operators in our analysis. So here we just show with two scenarios as an example. For example, we here scenario A and scenario B. Of course, in general, we should turn on all the operators and do a global fitting to check what's the impact of the EIC and also the LHC and also noise data. But here I just use the two scenarios as example to show the importance of EIC and LHC. For example, in here, I just use the scenario A example. The tau decay will give some constraint for the nearest two parallel space. This is U and D component. But you could find out you will only give some constraint in one direction. For example, in here, it will give some constraint for the anti-diagonal direction, but then no constraint for the diagonal direction. So after we include the HC for all the EIC, it could cross this direction. So it means that you want to constrain this kind of new physics operators. It is important to include both the known data and also the HC and also maybe the EIC. And the EIC, the limit is not very weak. It could be very strong. Okay, next I just give some summary. In this talk, I discussed the charge lepton fluorescence, and this thing is very important for us because it could relate to the neutron mass. So precise studies think that maybe we could get some hint of the neutron mass generation mechanism. And for the EIC, because this is a typical DS process, so the EIC is a good machine to probe this charge lepton fluorescence effects. And based on the sample analysis, we found out EIC is compactive and also compared to the HC and also the B factorials. So you want to give a global constraint for this charge lepton fluorescence operators. We also should include the EIC limit. Thank you very much.